Okay, so now that we have answered our focus question for the periodic table and periodic law, let's look at the development of the periodic table. So Anton Lavoisier listed the 33 known elements of his time into 4 categories. There's a picture of him there on the left, and the example on the right is his periodic table. Okay, it wasn't really much of a table, it was really more of a list. And he organized these based on what he thought the properties of these elements were. Okay. John Newland proposed a different organizational strategy, and he called this the law of octaves. And it didn't work for all known elements. So basically, he noticed that there was a repeating pattern of properties, and he noticed that about every 8 or so, or 7 or so elements, the patterns repeated, and that's what this image underneath of the text shows. So excluding hydrogen, it starts at lithium, and you can see the colors repeat, right? And so he said each of those is an octave of the periodic table. And he got a little closer than Lavoisier did, but he still wasn't quite there yet. Then we watched the video about Dmitry Mendeleev and how he organized the elements by increasing mass. And Mendeleev is really considered the father of our modern periodic table. He also saw a repeating pattern of properties, and when appropriate, he trumped his mass order with the by organizing those in their groups or families through their properties. So for example, there's a couple of exceptions in his table. One of those being tellurium and iodine, right? Tellurium is lighter, iodine is lighter than tellurium, but it fits better as a halogen than it does as the other group, the group that tellurium's in. So he placed that out of mass order, but also in the right spot. Because he based it on the properties rather than just strictly mass. And he knew there was more going on, but he didn't quite grasp what it was. And it wasn't until Henry Moseley came along and he discovered that each atom has a unique number of protons, and he did this using X-rays. So we also saw Moseley in the video, and he used this apparatus on the left. It's a vacuum tube, and it allowed him to just slide samples through the vacuum tube into that X-ray viewer, and it allowed him to look at the X-ray barcode for each of those elements. And he noticed that those created this staircase that you see on the right-hand bottom corner. Okay, so he used this to refine Mendeleev's table. He used it to explain why Mendeleev's table had exceptions to the mass order, because they weren't really organized by mass, they were organized by number of protons. Okay, and so once he understood that, he could really point out the missing elements. Like he knew element X had a certain number of protons, and element Z had another number of protons, and that there was a missing element in between. And so he was able to predict where those missing elements would be on the periodic table when they were found, even more accurately than Mendeleev. And so this was really revolutionary, because this is where the number on the periodic table meant more than just an element's place on the periodic table. This is where we really realized that it meant the number of protons. So remember, we say atomic number equals number of protons. That wasn't really true until after Henry Moseley made his discovery. Okay, and then the last thing is that we knew that there's 3 main categories of elements: metals, metalloids, and nonmetals. And this first thing where it says staircase right underneath the title of the elements categories, we're going to see what that staircase is at the end of this week, but not right now. So just know that metals are left of your staircase, metalloids are the staircase, and the nonmetals are right of the staircase. And if you ever see a color picture of the periodic table, you're going to immediately recognize what that staircase is. Okay. Metals are always shiny. They're malleable, meaning that you can smash them into sheets. You can change their shape by hitting them without breaking them. They're ductile, meaning you can draw them out into wires. They're conductive, which is why we have electrical systems using copper wiring in our houses. And then they have low melting points, but high boiling points. And that has to do with the way the electrons are arranged in metals, which we'll talk about later when we talk about metallic bonding. Metalloids are kind of a mix, so we're going to talk about them last. So non-metals are on the right hand of the staircase. Instead of being shiny, they're very dull. You can't hammer them into sheets or change their shape by hitting them without breaking them. They're very brittle. They're not ductile, meaning you can't draw them into wires. They're not conductive. They have very low boiling points and fairly low melting points when they melt. Metalloids, like I said, they're the in-between. So they have some properties of metals and some properties of non-metals. They can be shiny or dull. Some metalloids are malleable, some are not. Some are ductile, some are not. They are either semiconductive or conductive. Okay. Semiconductive means that they just conduct under certain conditions. The melting point and boiling point for metalloids vary, but they're always going to be higher than metals and lower than higher melting points than metals, lower melting points than non-metals. And the boiling point, it really depends on the properties of that particular element. If they're more like a non-metal, they're going to have a low boiling point. If they're more like a metal, they're going to have a really high boiling point. All right. I will see you in the next video.